Okay, let's get started. So I would like to welcome today Aritra Mitra, who is a PhD student here at Purdue in the Department of Electrical and Computer Engineering. So he works on designing distributed algorithms for estimation, inference and learning, network control systems, and secure control. And he's here today to talk to us about a new approach to distributed hypothesis testing and non-Bayesian learning. So with that, I will leave it to you.
Okay, so thank you for the introduction. And so this is joint work with my collaborator at Sandia National Labs, that's John Richards, and my advisor Shreyas Sundaram. Okay, and so this is part of what I've been working in my PhD. And I mean, so this is probably going to be an informal session. So please feel free to stop me in between, ask questions whenever you have any doubts. Okay. So I thought I'd get started with maybe a cartoon illustration of what this problem looks like. And have any of you seen this before, maybe? Okay. So it's based on an old Indian parable, and it's called The Blind Man and the Elephant. So what's happening over here is that you have 6 blind men, okay, and they're positioned at different parts of an elephant. And depending upon where they are, they're each hypothesizing regarding what the object is that they're in contact with. Okay, so for example, I mean, this guy is thinking it's a rope, some other guy on the other end is thinking it's a spear, but what you can see is that they all arrive at disparate conclusions. But the fact is that there is only one ground truth, that this object is an elephant. Okay, so the issue over here is that based on their limited information, none of them can unravel what the truth is. But presumably, if they all got together and exchanged information among themselves, they might have figured out what this object is. Okay, so our setting is somewhat related to this. So like the blind men in the previous slide, imagine you have a group of entities, okay, network of entities, where these yellow dots are the entities, and they're interacting with each other over a directed graph. Okay, so the black edges represent who can exchange information with whom. So for example, over here, this guy can send information to this guy, whereas between these two entities, they can each send information to the other. Okay, so you have a network of entities spread out over some network, and let's say you have m possible states. Okay, and you can call them hypotheses, you can call them possibilities, you can call them whatever you want. And the point is that there is only one true state. Okay, and we'll call that state the true state of the world. Now, depending upon what's true, each entity is going to see a pattern of signals, some private signals. And the goal of these entities is to figure out what's the true state that's generating their signals. Okay, so that's basically the setting. But the challenge over here is the fact that, like the previous example that we saw in the previous slide, none of these entities in general have enough information to figure out what's true entirely on their own. Okay, so for example, if you have, let's say, 100 hypotheses, maybe one agent at one corner of the network can tell you that, okay, it's not between 1 and 10. Some other guy at some other corner of the network can tell you, okay, it's not between 90 and 100. So each one of them can reduce your uncertainty by a certain bit, but they cannot reduce your uncertainty entirely. Okay, so what needs to happen is that there needs to be an exchange of information across the network for each agent to eventually figure out uniquely what's the true state. And why might we interested in this problem? It's because this has applications in a variety of settings. Okay, so you can think about these entities as individuals in a social network. So this platform might be, Twitter, Facebook, or some other, social media platform, and maybe these entities are discussing on some day-to-day issue. So for example, who do we vote for, what product do we buy, which restaurant do we go to, etc. Okay, and so you can think about there's a true event that's taken place somewhere in the network, somewhere in the world, and each one of them are trying to figure out what that is. And the private information that they get, you can think of that as maybe local news channels, Twitter or some other news agency. And again, what they need to do is that each one of them, looking at the piece of information that they have, they create certain beliefs about what's true and what's not. And when you talk to your neighbors or friends, your beliefs get shaped based on what they think is true and what they think is not true. And so the question is, what happens when these agents interact? How do their beliefs evolve? And is it true that as the beliefs evolve, they progress towards, do the beliefs concentrate on the true quantity, on the true state? Okay, and there's no reason to restrict ourselves to just social networks. We can think about engineered systems, where now these entities represent, let's say, a team of autonomous robots. And let's say that they've been deployed over some region, and their task is to figure out whether or not there's radiation leakage over the region. So in this case, M is 2. There are two possibilities. Either there is leakage or there is no leakage. So it's a binary hypothesis testing problem. And these agents are basically collaboratively exchanging information and trying to figure out which one of these is the true possibility. Okay, and likewise, you can also think about a statistical inference problem or a machine learning problem where you have M classes that can generate your data. Okay, but what you're trying to do is that your data might be high dimensional and your number of states might be very large. So you might want to parallelize your computation across multiple processors. Okay, so each processor is getting some data, and the goal of these processors are to exchange information and figure out what's the true data generating class. So you can think of this as a classification problem. Okay, so there's a variety of settings where this is applicable to. Now, so that's the key question. So how should information be, diffused across the network? How should we aggregate information so that each agent, although they start out partially informative, eventually are able to figure out what's the true quantity? Okay, so is everyone more or less clear with the setting? Okay. Now, the question is, why do we now care about security and resilience over here? Okay, and I think most of you would have heard of fake news and false news and stuff like that, right? So then the point over here is that let's say that there are some extremists or stubborn individuals who want to convince you of an alternate reality. Okay, there's something true that's taken place, but they want to convince you of something else because of their own agenda. Okay, and it's exactly a similar setting where now some agents don't behave as they should do, but they behave with selfish interests. Okay, and there's lots of work that's looked at this. And for example, this is a very recent research that's conducted by researchers in MIT Media Lab. And what they found out is that, so this is empirical, by the way. So they took a lot of data from Twitter and they sort of analyzed that false data tends to spread much faster on Twitter than true data, true news. Okay? And so I'll just quote something from here because I think it's relevant. Falsehood diffused significantly farther, faster, deeper, and more broadly than the truth in all categories of information. Okay, so this is exactly relevant to what the setting that we studied right now.
Isn't sometimes the intention of false news to make it to get it spread faster?
Don't forget to use the buttons. Yeah.
So isn't sometimes false news made so that just to spread and get popularity or something like that? So does this account for that bias? Because
no, so this is not exactly that. So this is saying that out of your many possibilities, whatever is true, you have certain entities that are trying to convince you of a different possibility. Okay. So there might be ways of formulating it as something that you're saying, but that's not exactly the same situation over here.
Okay, thank you.
Okay, so that's one of the reasons in the context of a social network why you might be interested in this. But again, for engineered settings, you can think of these as faults. You can think of these as attacks on certain parts of the network, sensors, etc. Okay, so that's why we care about security and resilience in these settings. Okay, so then so this is basically the question that if you have misbehaving entities, then how should you process the information that you're getting? You don't know who's bad, who's good. You don't know who's telling you, factual information versus something that's not true. So then how do you process the information that you're getting from your neighbors? And how do you look at the own information that you're getting, the local information that you're getting, combine them in some way so that eventually you're still able to learn what's true? Okay. So then without further ado, let's take a look at the setting in a more formal way. As I said, you have m different states. We'll call them the m hypotheses, labeled from 1 to m. Okay. only one of them is the true state. We are going to call it the true state of the world and denote it by theta star. Each agent in a network is going to receive certain private signals that I'm going to denote SIT. I is the index for the agent, T is the index for time. Okay, so it's a stream of signals. And to make our lives easy, we'll assume that this stream of signals is IID, okay, independent and identically distributed. Now, for each hypothesis, each agent is going to have a likelihood function, a conditional likelihood function. What does this mean? So what it means is that Li Wi theta is essentially the probability that agent I sees the signal Wi given that theta is the true state. Okay, and I'll make this precise with some examples. Okay, so it's basically a distribution over the signal space of the agent conditioned on each of these thetas, each of these states. Okay. So then what does an agent do? It has these conditional likelihood functions with it, and it has a belief vector. The belief is essentially a distribution over the hypothesis set. So initially I'm clueless. I don't know what's true, what's false. So there are m possibilities. If I'm clueless, let's say I have a uniform distribution over the states, meaning that I have a 1 over m belief on everything else, or everything. Okay, so that might be something that you might do. You might have some bias towards one, but let's say you have a 1 over m belief on all of the states. What you want is that you want to recursively update your beliefs as a function of what you see and what your neighbors tell you, so that in the limit, as time goes to infinity, your belief should concentrate entirely on the true state. Is that more or less clear to everyone? Do you have any questions? Okay, so this is, and because this is a stochastic setting, the signals are random, so we'll think about convergence in some stochastic sense, but that's not really important. Okay, so this is exactly what we want. We want to come up with some sort of a belief update rule and exchange rule, so that which guarantees that the beliefs of all the agents converge to 1 on the true state. Okay, so your belief on the true state should go to 1, which basically means that your beliefs on everything else should go to 0. And almost surely basically means that this should happen with probability 1. Okay, so that's the thing that we're saying over here. And I mean, so this is not a new problem. I mean, because the setting is so widely relevant, it's been looked at by several researchers across different fields. So you have, people from ECE, computer science, economists, sociologists, and a variety of other, groups of people who have looked at it. So what we mainly propose is a learning rule that does not rely on belief averaging. So what do I mean by that? I'll make this precise again. And typically what rules do is that I have some belief, you have some belief, let's average these. Okay, let's average these and let's, think of that as a new belief. But what we'll show is that these belief averaging rules can tend to slacken your process of learning. So if you average, it might be that you end up learning, but learning really slow. So there are better ways to do this, which really give you faster learning rates. So with this new learning rule, what we basically show is that it works under minimal requirements on the observation model and the network structure. So clearly you need some conditions to hold, right? So for example, let's say you have a network where you have some informed agents at one corner, you have some non-informed agents at some other corner, but there is no path linking them. So then clearly the non-informative agents have no hope of getting information from the informative ones, right? So you need clearly some conditions on the network structure, and you need some conditions on the observation model. And so what we are saying is that the conditions under which our rule work are minimal. So this is necessary and sufficient for any rule to work. And secondly, for the case where you have agents that act adversarially, meaning that they don't behave as you would expect them to behave, we show that there's a way to sort of extend this rule and come up with one that's computationally efficient, and it still allows all the good agents to learn what's true with probability 1. Okay, and so you might ask, what is the model that we use for modeling adversarial behavior? So it's a very general model known as the Byzantine adversarial model. So it basically got introduced by the computer science literature, community in the 1980s. But it's a very strong adversarial model which basically allows each adversarial agent to act arbitrarily. In the sense they can send you any information that they want. They can send different pieces of information to different people. They can choose not to send any information at all. So you can have any adversarial behavior that you can think of, it's incorporated by this model. And so then you can use that to model, stubborn agents or extremists in a social network, or you can think of these as faults or attacks in an engineering system. Okay, and the final point is that, as I said, with this new learning rule, you also get a strict improvement over the learning rate. So the learning rate is how fast you learn the truth. Okay, and this is just a reference for the work. I'll again come to it later in the talk. Okay, so that we are all on the same page, let's try and understand what is a likelihood model. Okay, so let's suppose you are looking at just one single agent, and there are three possibilities: theta 1, theta 2, and theta 3. Okay, so then this matrix L is the likelihood matrix. And let's say that the signal space of each agent is heads or tails. So it only sees two signals, either a heads or a tails. Or you can think of this as seeing a 0 or a 1, just two signals. Okay? So then each row is a conditional likelihood function. What the first row is telling you is that if theta 1 were the true state, then this agent would see heads 75% of the time and tails 25% of the time. What the second row is telling you is that if theta 2 were the true state, then this agent would see heads 50% of the time, tails 50% of the time. So each row is a conditional distribution, and each column is basically telling you the probability of seeing the corresponding signal under that hypothesis. Okay, so then what you can see from this is that regardless of whether theta 1 got realized or whether theta 3 got realized, this agent would see 75% would see heads 75% of the time and tails 25% of the time. Okay, so if theta 1 were the true state, if you look at the pattern of signals, then you would see heads showing up roughly 75 times in 100 throws. Similarly, even if theta 3 got realized and you ran this experiment for 100 iterations, you'd expect to see heads 75 times. Right? So in that sense, we'll basically say that these two hypotheses are observational equivalent from the perspective of this agent. Okay, so there is a way to make this more formal, and the idea behind that is that you basically look at some notion of distance between two distributions. Okay, so there are various ways to define distances between distributions, and this basically comes from information theory. We'll look at one that's relevant to our cause. It's basically known as the Kale divergence between two distributions. And essentially what it's capturing is that, let's say you have two distributions. You have data generated by distribution 1. You have data generated by distribution 2. You look at these data. Can you by looking at this data tell that these data are coming from two different distributions? And to what extent are you able to tell that they're coming from different distributions? That's essentially the notion of a Kale divergence. So it basically, think of this as a black box. It takes in two distributions, spits out a number. The larger the number, the more your ability to tell them apart. The smaller this number, the less your ability to distinguish between them. Okay, so the formula and everything else is irrelevant. Don't need to look at that. Okay, so what are we interested in? We are interested in knowing, given two distributions, what does it mean for the Kale divergence to be 0 between them? If the Kale divergence is 0, then essentially you can't tell these two distributions apart. They're exactly the same to you. And if it's strictly positive, then you can tell apart these distributions. Okay, and the Kale divergence is always non-negative. So then using this concept, we can formally say when two states are observational equivalent to an agent. So let's think about two possibilities, theta m and theta n, that belong to the space of thetas. And the corresponding likelihood models are Li conditioned theta m, Li conditioned theta n. Okay? So then if these two distributions have 0 Kale divergence between them, then these two states are observational equivalent from the perspective of this agent. Okay, so this is basically the point of a KL divergence. And we'll see this coming up later in the talk. Okay, so then as I said, I mean, this is not a new topic of research. There's been lots of work that's gone into this. And so before I present to you what we do, it's instructive to sort of at least take a look at what others have done in the literature. Okay, so this is just a brief overview of what kind of rules exist in the literature. Okay, so this model that we are studying was basically introduced in 2012. So it came out in a journal called GEB, Games and Economic Behavior. So as I said, it's been looked at by a wide array of communities. Okay, so then what they said is that so this is basically an inference problem, right? You're seeing some signals, you want to figure out what's the thing that's causing the signals that you're seeing. So what's the standard paradigm for doing that? Bayes rule, right? So you see a signal, you ask yourself, what's the probability that I'm seeing this signal given θ1, given θ2? You have a prior, you look at get a new piece of information, create a posterior. The only difference over here is that you have a prior, but so do your neighbors in the graph, right? I have some beliefs, my neighbors have some beliefs. How do I take those beliefs and do something with it? So then, well, I mean, you might ask yourself, what do I do? Let's average, right? That seems like something that you might do. No reason for doing it, right? But that seems like something that you might start off with. So then they do exactly that. So let's say that what's happening over here? So this is standard Bayes rule. So this notation over here is telling you mu I t theta is the belief of agent I at time t on theta. So you take your belief at time t, you multiply that with the likelihood of seeing the signal that you see at time t plus 1, okay, given theta, and then you create a posterior. But then what you do, you don't stop there. You take your own posterior and then basically combine it linearly with the priors of your neighbors. So essentially you're taking a convex combination of your own posterior and the beliefs of your neighbors or the priors of your neighbors at the previous time step. Alternatively, what you could have done is that you could have collected the beliefs of all your neighbors at time t, taken a linear average of them, thought of that as a prior, multiplied that with your likelihood, created a posterior. So essentially you're doing linear averaging of beliefs over here, okay, to create your posterior at the next moment. So then why stop there, right? I mean, if you can do linear averaging, let's do geometric averaging. So that's something that other people came up with. So this is later work in 2016, 2017. And what they're doing over here is that you collect all the beliefs of your neighbors in the graph. So these are the people who you can talk to in the graph. You collect the beliefs of the neighbors, take a geometric average of these beliefs. So the Wij is essentially the weight that the ith node places on the jth node. So this is how much importance I give to the jth node if I am the ith node. Okay, so these weights are essentially when you're doing a weighted geometric averaging, these are the weights that show up in the weighted geometric average. So you take a weighted geometric average of the beliefs of your friends in the graph, think of that as a prior, multiply that with your likelihood, create a posterior. And the term in the denominator is just a normalization term. Your belief should add up to 1, right? So you need to normalize it. So that's what's happening in the denominator. Okay, so what's common to both of these approaches is the fact that you either take a weighted linear average of your beliefs or you take a weighted geometric average of your beliefs. And it was shown in both of these cases, both of these rules work. Okay, so both of these rules work in the sense that if you keep doing this repeatedly, this creates a sequence, right? A sequence of beliefs indexed by time t. So both of these sequences are consistent in the sense that the beliefs would eventually converge to the true state in each of these cases. But what's different is the fact that in one you get faster convergence, in one you get a little slower convergence. So geometric averaging gives you faster convergence, linear averaging gives you a little slower convergence. But the question is that, do we really need to do averaging for this problem? And if you are interested in, distributed algorithms is a huge area, right? You have problems like consensus, distributed optimization, estimation learning, etc. And the most common, the simplest version of that is a consensus problem. where you have lots of people in the room, they each start out with some opinions, you average, and eventually you want the opinions to converge. The reason why you do averaging is the fact that if you can do this, then you can sort of relate it to the consensus problem, use tools that you have over there to do an analysis for this, and things sort of work out. And you'll see this is a common theme across optimization, consensus, learning over networks. But the point that we are trying to make over here is that every problem is unique, and so you need to sort of think about each problem uniquely. So then what's sort of the problem with averaging? Let's say that you have two agents, okay, 1 and 2, and you have two states, theta 1 and theta 2. Let's say that the true state is theta 1. Let's say that agent 1 is informative in the sense that if it gets enough signals, it will be able to tell that theta 2 is false. And 2 is completely uninformative in the sense that its signals are useless. So it's totally reliant on 1 to inform it about what's true and what's not. So now let's suppose that at some point in time, agent 1 is getting informative signals, so at some point its belief on the false thing is really low. So maybe it has a 0.1 belief on the false thing. Whereas agent 2 needs more convincing. So its belief on the false thing is pretty high. Let's say it's 0.9. So then what's the objective of agent 1? It wants to drag down the belief of this uninformative agent on the false state. Right? It wants to pull its belief down on the false state. But what happens if you average? Each of them end up with a 0.5 belief. So then in the process of me, if I am the informative agent, in the process of me trying to drag down the belief of an uninformative agent, my own belief on the false thing has gone up. Do you see what I'm saying? That's not what I want, right? So I should be able to convince you what's false without compromising my own ability to tell what's true and what's false. Here, I'm able to drag your belief down, but at the compromise of me also putting my, having a higher belief on the false thing. Eventually, this works, but what you will see is that you see oscillations because, I'm trying to convince you of something, you're trying to convince me back, we are fighting because of the averaging, and our beliefs oscillate, and so although we converge, it takes longer for us to converge. Does that intuitively sort of make sense? Okay, great. So this is exactly what I just said. So then the question is, so the point is that averaging can dilute the rate of learning, and can we get rid of this effect? Okay, so the first thing that we'll say is that, okay, let's forget about averaging. Let's go back to a standard Bayes rule. Okay, let's think about the centralized case where you just have one agent in the graph. What do we know from Bayes rule? Let's first try and think about that. So a Bayes rule is just this, right? Let's say that you have just one agent. It's sequentially applying Bayes rule, taking its belief on theta at time t, multiplying it with the likelihood of seeing the signal that it sees at time t plus 1, creating a posterior. And this is a normalization term. What happens if an agent applies Bayes rule? That's the first question. What happens is that if the state theta is not observationally equivalent to theta star, which means that this agent can tell the difference between the true state theta star and theta, then its belief on this false state theta is going to go to 0. That's just a property of a Bayes rule. You can prove it. It's not that hard to prove. You can prove that the belief of this agent on this theta is going to go to 0. Whereas if it cannot tell the difference between theta star and theta, then its belief on this false state theta is forever going to remain bounded away from 0. So if you can tell the difference between what's true and what's false, then your belief on what's false is going to go to 0. If you can't tell the difference, then you will have a non-zero belief in the limit on the false state. But what's important to note over here is that each agent, looking at just its own signals, can potentially eliminate a certain subset of the hypothesis that it can eliminate on its own. I may not be able to eliminate everything, but I'll still be able to eliminate, let's say, something, right? Maybe I'm able to eliminate a subset of the states. That's the key point over here. And just to make this precise, if we go back to the example that we saw earlier, you can see that this agent can't tell the difference between theta1 and theta3, right? So then let's say if theta1 is the true state, then what's going to happen is that its belief on theta2 will go to 0 because it can tell the difference between theta1 and theta2. But in the limit, it's going to be confused between theta1 and theta3 because they are observationally equivalent to it, right? So it will basically have a 0.5 belief on each of them in the limit. But what we should note over here is that nonetheless, it's still able to eliminate one of these. And the question is, how can we leverage that to our advantage? Do you have any guesses regarding what we're going to do? So the idea is that, okay, let's say that you have two belief vectors side by side. You know that there's going to be a 0 on one of these entries eventually, corresponding to one agent being able to eliminate that hypothesis eventually. What do I do to propagate that 0 from my belief to someone else's belief? Why don't I take the min of the beliefs? So if one of them is going to 0, it has to drag down the belief of the other one to 0 as well. Okay, so what you want to do is that there's a little trick over here where we want to first ensure that whatever I can do on my own, I retain my ability to do that. How do I do that? I maintain a local belief vector. What do I mean by local? This is updated without any neighboring influence. So this is purely based on the signals that I see, and it's not contaminated by anyone in the network. I'm not talking to anyone else in the network when I'm updating this local belief. So what that means is that if I'm able to eliminate something on my own, that's going to show up in the local belief vector. I'll be getting certain zeros for those entries in my local belief vector. And then there are certain things I can't tell on my own. And so then I need to talk to my neighbors in the graph, right? So that's going to be captured through an actual belief. So this is a corrected version of the local belief, let's say. So what do I do to update my belief on a certain state? In this vector, I take the minimum of my own local belief on it and the actual beliefs of my neighbors on it. Okay, so I'll again explain that in a bit. Okay, so basically you take the minimum of your own local belief on something and the actual beliefs that you get from your neighbors. So let's make this precise. So there are two steps. At each time step t, an agent is going to update its belief on a state theta as follows. There are two steps. In the first step, it creates a local copy, a local belief, based on exactly the same Bayes rule that we saw. And notice that there is no influence of the network over here. Okay, so in the next step, what it does is that this actual belief on theta is nothing but the minimum of its own local belief on it and the actual beliefs of its neighbors. So let's see why this might work. So let's say for every false hypothesis, there is at least one agent in the network who can tell that it's false. If not, then the entire network remains confused regarding that state. So for every false state, you need at least someone in the network at some fringe, at some corner, to be able to tell you that that's false. Think about that node. For that node, its belief, local belief, is going to be going to 0 because it can tell that theta is false, some state theta is false. If its local belief is going to 0, regardless of what its neighbors are telling it, because they have a min over here, if this goes to 0, regardless of what this is, your neighbors can have very high beliefs on this false thing. But because this is going to 0, it's going to drag your own belief on this thing to go to 0 as well. So if you can do something on your own, when you talk to your neighbors in the graph, you don't lose your ability to do that thing, right? So next what you want is that, okay, my actual beliefs are going to go to 0 on this. I want my neighbors' beliefs on this to go to 0 as well. But that's going to happen as well, right? So think about the immediate neighbors of this node. When they update this quantity, this belief is going to show up in their update rule, right? So then if this is going to go to 0 for one of their neighbors, it's going to drag down the beliefs of their neighbors as well. Right? So when my neighbor updates my belief, updates its belief on a certain state, it's going to use my belief. Because my belief is going to 0 and it's doing this min thing, my belief is going to show up over here, and because this is going to 0, it's going to drag down the belief of my neighbor as well. And when its belief goes to 0, it's going to drag down the beliefs of its neighbors as well. And so this creates a process of cascading beliefs on each false state. But you might ask the question that, can't this happen with the true state as well? Could it be that because this is a random process, during some transient phase, you see bad signals? And because you see bad signals, your belief on the true thing temporarily goes down. As soon as it goes down, someone is taking a min with respect to that. That drags their belief on the true thing to go down as well. Can it create a cascade of low beliefs on the true state? If it did, then this would not work, right? So the answer is basically no. You can prove that with probability 1, the beliefs of all the agents on the true state are eventually going to remain lower bounded by some quantity. Why is that the case? The reason behind that is that the Bayes rule helps you eliminate false hypotheses, but if you can't tell that something is false, it's not going to place a 0 belief on it. So if you can tell something is false, it's going to place a 0 belief on it. If you can't tell something is false, it's never going to place a 0 belief on it if you start out with a non-zero belief on it. So then at some point, the local beliefs of all the agents on the true thing are never going to go to 0. They're going to be some quantity. Maybe if there are 100 states and I can eliminate 50 of them, then my belief on the true thing is within the other 50, right? It's never going to place a 0 belief on any one of those 50 states. So my belief on the true thing never goes to 0 in the local belief vector. So then what is it that's going to drag this down? At some point, this quantity is eventually going to be lower bounded by something for all the agents in the network. As soon as that happens, this will sort of also stop decreasing, because there is no cause for this guy to reduce its belief. The cause is encoded over here, which is coming from the signals. If the signals don't cause you to reduce your local beliefs, this stops decreasing, and then this also stops decreasing basically at some point. Okay, and this is just an informal argument, but there's a way to make this mathematically precise. But is everyone sort of convinced about why this might work? So this is preserving the intrinsic discriminatory capabilities of an agent. So whatever this agent could do on its own, it's preserving its ability to do so. Whereas this is enabling you to facilitate, it's facilitating propagation of low beliefs in the false hypothesis. Okay, so basically this is saying that for each hypothesis, just listen to the neighbor who has the lowest belief on that hypothesis. So, okay, in the interest of time, I'm going to skip this example. I might come back to it if there's time left. So the main result over here is that, under very standard assumptions. So what are these assumptions? The first one is telling you that for every pair of hypotheses, you need at least one agent in the graph who can tell them apart. So for every pair, you need at least one agent who can distinguish between them. You need some notion of connectivity, which basically says that between every pair of agents, you need a path connecting them. And then what this is saying is that you need to start out with non-zero beliefs on each state. You can start out with a very, very low belief on the true state, but as long as that's non-zero, that's good enough. And given that, what we can show is that for every false hypothesis, this quantity is essentially the rate at which your belief on this false thing is going down. It's an exponential decay, and this quantity is essentially the exponent of decay. So this is so if you have a e to the power minus alpha t decay for theta, this is alpha. Okay, and that exponent is in general a function of time. This is saying that eventually everyone in the network will be able to eliminate theta at a rate that's at least the best scale divergence across the graph. So this quantity is the discriminatory power of agent V between these two states. You look at all the agents in the graph and the discriminatory powers, take the max, and that's the rate at which you will be able to eliminate the state theta. Okay, so whatever is the best rate across the graph, all agents will be able to eliminate each false state theta at that rate. And so how does this compare with existing approaches? If you do averaging, you get an average of the rates, where the weights that show up in the average are essentially something known as the centrality of an agent. So a centrality of an agent can be sort of, you can think of it as like who's influential in the network. So if I have a lot of friends, I might be very influential. Okay, so what happens over here is that the rate at which you reject a state theta is a convex combination of how informative am I and a function of how influential am I. If I'm very informative as captured by Ki and I'm very influential as captured by Vi, then there's going to be a positive matching between these two quantities and I'll be really able to create an impact in the graph. But you can imagine if you have a reverse matching, the most informative agents are the least central, so they're the least influential people in the graph, then your rate of convergence will really be slow. What our result is saying is that it doesn't depend on the network size nor the network structure. So that doesn't show up at all. Okay, so it's saying that no matter how you allocate your information across the graph, no matter what the size of your graph is, you'll still get the same rate, which will be the best rate at which you could eliminate these thetas. So a quick example, let's say you have like a star graph on n nodes, okay? The node at the center is the only node who's getting informative signals. And you have two states, let's say theta 1 and theta 2. So then what this is saying is that this is just a comparison, and the true state is theta 2. So then this is comparing our rule in orange with the linear rule in green and the log linear rule in blue. The case on top is when you have 5 agents on the graph, and you can see that I'm plotting the beliefs of agent 3 on the true state theta 2, and you can see that the orange converges faster. And if you plot the convergence rates, it's essentially, the black line is what we expect it to be in the limit, and this is sort of hovering around there. Whereas for the other two rules, the rate gets scaled by the size of the network. So if you have a really large number of nodes in the graph, it's going to really bring down your rate of convergence. So in this case, you have n equal to 10. The rate of convergence from this has gone down, whereas it's the same for our rule. Okay, so this quantity is essentially the exponent of decay. This is what we expect it to be in the limit for our rule, and this is what we expect it to be for the other two rules. So what this is saying is that learning rate is going to scale inversely with the size of the network for the existing rules, but it remains the same for this rule. Okay, so now let's move quickly to the case where you have miscreants in the network. You have people who are spreading misinformation, and as I said, this is any rule that you can think of is sort of going to break down because of this. So you need to incorporate some resiliency into your algorithms if you want to take care of, if you want to account for these attacks. Okay, so then the model that we're going to look at is something known as the Byzantine attack model, okay, where we'll assume that an adversary has complete knowledge of the system, the network, etc., and it can act arbitrarily. But we need to place some assumptions. So we'll say that it's an F local model, meaning that in the neighborhood of any good node, you can have at most F bad guys. Okay, so in everyone's neighborhood, you can have, if you think about any good node in the graph, it will have at most F bad guys in its neighborhood. But you don't know who they are, and they can do anything that they want to. Okay, and let's denote the set of good nodes by R. And the question is, and what do we do? So there are two things that we need for this to work. Essentially, you need redundancy in the communication structure. You need redundancy in the information structure. So what do I mean by that? Let's say you have a lot of informative agents and some uninformative agents over here. You need to disseminate information from these guys to these people. But imagine that they're going through a bottleneck in the graph. And those are precisely the nodes that get compromised by the adversaries. So then you can never sort of transmit information securely from these guys to these guys, because the nodes in between sort of act as a bottleneck or a cut in the graph. So you need enough disjoint paths linking the informative agents to the uninformative agents. So that's communication redundancy. At the same time, you need information redundancy. Why? Because if you have too few informative people, and those are precisely the nodes that get compromised, then you have no hope of learning, even if you have multiple paths across the graph. So you need both of these quantities. So then we introduced a graph property, which again I'm not going to go into. And the point is that if this graph has this property, then the algorithm that I'm going to show now is going to work. And the algorithm is again very simple. Again, each node is going to run a local belief vector, as it did before. But now the question is that it knows that some people in its neighborhood might be bad. It doesn't know who's good, who's bad. So what it does is that if it has very few neighbors, so if the size of its neighbor set is smaller than 2f plus 1, where f is the maximum number of bad guys in its neighborhood, it's not going to trust anyone then. So it's saying that if I have too few neighbors, I'm not going to listen to anyone. My actual belief is just going to be my local belief. I'm not going to pay attention to anyone in the graph. But if it does have greater than 2f plus 1 neighbors, then it's going to collect the beliefs of its neighbors. It's going to throw away the highest f beliefs, the lowest f beliefs, take the rest of them, and then do the min operation over this reduced set of beliefs. So earlier it was doing this min with respect to the beliefs of all the agents in the neighborhood of this agent. Now it takes only the ones that are the most moderate. It throws away extreme beliefs, collects the moderate ones, puts them inside this set, and then takes the same thing that it did before, but this min is now over the smaller set. So it's a fairly intuitive thing to be doing, right? Reject extreme beliefs, take the moderate ones, do whatever you were doing before. And again, we show that if the graph has some property, so it's a combination of the two things that I said. The property encapsulates redundancy in communication structure and redundancy in the information structure. And that's something that we call strong robustness, basically. If that's true, and each good node in the graph starts out with a non-zero belief, then every good node will eventually learn what's true. Note that we place no conditions on the beliefs of the bad nodes. So if we were doing exactly what we did before, it's very easy to break this algorithm, right? What would a bad node do? It would immediately place a zero belief on the true thing. As soon as you take mins, a zero belief on the true will eventually lead to zero beliefs for everyone else. So your bad guys can be crazy. They can put zero beliefs on the true thing. They can do whatever they want. But the fact that you're sort of, throwing away the extreme beliefs and then doing this min operation helps you. So that still enables you to learn, provided you have this graph condition satisfied. Okay, and this is a stronger condition than just saying that I have 2f plus 1 people in my neighborhood. Because you might think that if I have 5 bad guys, I need at least 6 good guys, right? So there needs to be a veto sort of a thing. But that's not, this graph condition is not just that. It's a stronger condition than just having 2f plus 1 in degree. Okay, so that's essentially the point, and this graph property is not a terrible property. It can be checked in polynomial time. So you can take a network, you can see if this network has this property. If it does, then this rule is going to work. Okay, so that's sort of the take-home message. Okay, so maybe I'll just take a couple of minutes to explain the simulation slide that how much time do I have? Not a whole lot? Okay. Okay, then I can probably maybe skip this, I guess. So it's just a video of some robots moving around and simulation and how their beliefs evolve over time. So I can skip this maybe. So yeah, the take-home message is essentially the fact that Yeah, so we proposed this new learning rule. We showed that it allows you to learn things really fast. And the way it's different from existing rules is that it doesn't average. It does a min. And we showed that the advantage of doing this sort of a thing is that not only do you get fast learning rates, you can easily modify it to account for adversaries in the graph, adversaries in the network. Okay, so that's essentially what I have. And then there are lots of potential for ongoing work. You can think about when two people are talking over a network, you might have that the link that you're using has limited bandwidth. So then you can't send out information in the, it's in its proper form, with high fidelity. So then at what data rates do you need to transmit this information so that you can still do this, perform this inference task with certain level of accuracy? Okay, so that's sort of like a communication efficient thing. And then you can have uncertainty is in your model, right? So do I know my likelihood model's functions exactly? Or do I know that, there's somewhere around some ball centered at some nominal likelihood function. So there might be uncertainties in the likelihood models. So that again might be something that is potentially interesting. Okay, and so with that I'll conclude. And yeah, if you have any questions, please feel free to ask me.
If you have questions, use the little mic button.
Good.
When you said, like, for example, if you have rogue agents in the network, and a lot of them have 0 values, if you take the minimum value, your beliefs tend to go to 0. In that case, you were telling that you remove the extreme values and take the moderate values, right? So isn't that similar to averaging then? If you remove the outliers and take...
But after you remove the extreme values, you're not taking an average of the rest.
Right.
So after you remove the outliers, what do you do after that? Do you average or do you do something else? So we are saying that even after you remove the outliers, right, you're not taking an average of the remaining values. You're still using the same algorithm as before. Earlier you were taking a min over all the beliefs over your neighborhood. Now you're taking a belief over only the beliefs that lie in this moderate set after you've rejected the outliers. You could have alternately taken an average, which would have then brought you back to the existing rules.
Right.
But we're not doing that because it's not clear if you throw out the outliers and take an average, whether that's going to lead you to convergence. Whereas with this, it's so easy to prove that if you do the same thing that we were doing before, but on a reduced set, instead of taking the min over the entire neighborhood set, take a min over just, the moderate set, basically. The set of neighbors who have moderate beliefs. That gives you convergence. It's not clear if you do averaging, whether you'll still get convergence after you've thrown out the outliers.
All right. Yeah, thank you.